Hello everyone, my name is Mania and I'm a PhD student at Northeastern University. Today I'm going to talk about workflow motif, an abstraction for debugging distributed system. And this is a joint work with Northeastern, BU, Red Hat, State Street, and Tufts University. I want to start the talk with constructing how we build distributed systems versus how we debug them. Today, distributed systems are amazingly large scale and complex, and the way we are able to build this complex distributed system is by leveraging abstractions. Abstractions allow developers to build really complex distributed systems out of simpler building blocks. And how they do is that they mitigate the amount of complexity that developers should deal with. Example of abstractions are the APIs that we are using, or the libraries that we are using for building distributed systems, or it could be, for example, using smaller building blocks to build larger distributed systems. Another example of abstractions are the data center architecture that consists of different layers of abstractions. So these abstractions allows developers to hide the complexity of the underlying layer and build them more easily. So in contrast, when we debug distributed system, we usually have no abstraction, and we usually have less sophisticated abstraction. In fact, the de facto approach to debug this distributed system is to use no abstraction whatsoever. We use raw logs that we might take from the system, or we might use raw traces that shows the graph of distributed system activity, and which shows how distributed systems perform a request. This extreme mismatch between how we build distributed systems versus how we debug them can be challenging and could cause performance debugging and debugging distributed system very hard. What we observed is that traces shows repetitive pattern within and across many requests. And these patterns are repetitive building blocks of how request is executed through the system and how distributed systems behave. We believe that by understanding the performance behavior of this pattern, we are able to make engineers to discuss about the performance characteristics and their expectations of the system. And it could address a wide range of tasks. In this work, we are exploring the utility of extracting these repetitive patterns from the traces of distributed system, and we build a novel abstraction for diagnosis tool called workflow motif. Workflow motif describes frequent processing patterns in the workflow of how requests are executed through the system along with their performance characteristics. And these workflow motifs are essentially the building blocks of distributed application runtime behavior. Different permutations of these workflow motifs are largely make up how request is processed by the system. An example of such processing patterns are, for example, the work done by distributed system through leader election. And how workflow motif helps engineers is by hiding the complexity of the underlying layer and eliminating the irrelevant problems to a given problem. I want to explain the workflow motif using an example from a workflow of write request to a distributed storage system called Ceph. And how this work is that workflow motif can find two types of motifs here. The top one shows the work done for metadata operation, and then the bottom one shows the frequent pattern that is observed for the trivial replication to the data nodes, to the OSD nodes. And then we discussed that workflow motifs are composable, which means that larger workflow motifs consist of smaller workflow motifs, and also workflow motifs consist of the performance behaviors of those motifs. This allows us to discuss the performance behavior of each frequent processing pattern individually instead of looking at the entire trace and discuss the entire trace at the same time. The key enabler for identifying workflow motif is end-to-end tracing tools or workflow tracing tools. And here is the basic explanation of how this workflow tracing tool works. This figure shows the deployment of distributed storage system along with the table store on top of that and the client application that access to the table store. So to capture the workflow-centric tracing infrastructure use trace points, and trace points are embedded within the distributed services code base. These trace points are added either dynamically to the code or they are embedded into the common libraries or could be enabled or disabled through the execution of the system. And these trace points have unique names and record the arbitrary low-level parameters of the system, such as CPU usage or disk usage or, for example, the queue length. They could capture different type of parameters and configuration parameters of the system. And then when a request is executing, tracing infrastructure propagates some context. We call them metadata propagation along with the request. And this allows the distributed tracing tools to restruct the behavior of the system and build the workflow of how request is processed through the system. For example, on the right side, you can see the workflow of writing to the HDFS, which is a distributed storage system. And our approach is to build workflow motifs by using frequent subgraph mining tools. Frequent subgraph mining tools are finding frequent patterns within a large corpus of traces and a large corpus of graphs. And these tools use a metric called support level for defining the frequency or the interesting frequent patterns. And these algorithms are widely used in DNA matching or in chemistry component, detecting similarities in chemical components. And they are usually expensive, both in terms of storage and in terms of performance. So our goal here is to adapt these tools to our specific domain problem. Here is software components for building workflow motifs. Underneath, you can see this distributed system. For example, here is a distributed storage system, and then on top of that, there is the end-to-end tracing infrastructure, which captures the workflow. Workflow motifs retrieves traces from the trace database, and then using frequent subgraph mining tools to extract the frequent patterns and filter the frequent patterns based on the required specification of the user. And then we enable querying to this corpus of motifs, or we enable users to annotate those motifs. And different use cases could be contrasting different execution traces or identifying anomalies among them. We can use them for identifying optimization. For example, we can look at the traces, we can look at the workflow motifs that has the largest performance variation and then choose them for optimization. Or we can use it for application comprehension. Now I want to discuss how we want to use frequent subgraph mining tools to fit them to our requirement. And I want to discuss our requirement first. The first requirement is that workflow motifs should preserve the work that is done, the ordering of the work that is done in the system. This means that in some of the traces, we observed that there is the similar work that is done through the workflow of the system, but the ordering is different. And in some cases, some of them are frequent and some of them are not frequent. So we expect our frequent pattern mining tools to be able to detect this behavior. The second thing is that workflow motifs are frequent across and within traces. This means that there are some frequent patterns that are happening among a large subset of traces, but few number of times, and there are some frequent patterns that are happening within a smaller number of traces, but many, many times within those smaller set. So our frequent subgraph mining tools should be able to capture both of these behaviors. And the third characteristic is that we have to add the performance characteristic metrics to the frequent subgraph mining tools to be able to report it as an output of the workflow motifs. So we go over 5 frequent subgraph mining tools. We go over FSG, which is a joint-based method, which means that it's start from 2 nodes and then add another node and expand the graph as much as possible. It doesn't consider edge order, or it doesn't preserve the ordering, so it is not point of our interest. And also it is looking for graphs within a corpus of the traces, and it doesn't look for across traces. The second one is Gaston, which is a pattern growth, and it starts from a node and expand that node as much as possible and build the largest graph that it could. The good thing about Gaston is that it starts from passes, and then it looks for trees, and then it looks for graph, which makes it more practical in our approach. Unfortunately, it doesn't support edge order, and it looks for frequent patterns across many graphs. We look at Grammy, which is based on FSG, and it enables lossy frequent patterns, which means that you can find frequent patterns that are not exactly matching together, but with some differences, we can consider them as similar frequent patterns. And then Arabesque is a distributed approach that currently does not support the edge ordering, but it is based on the Grammy, and it is a distributed model, which is helpful for having a scalable approach. And ASAP provides sampling within the frequent subgraph mining algorithm, which means that it doesn't require to find the entire graphs, and it only looks for a subset of them. Now I want to discuss the preliminary results we got from HDFS traces. We captured some, we ran some benchmark on top of HDFS, and we captured some traces. And we ran Gaston on top of those traces. And we were able to capture two motifs that were interesting for us. The left one shows the motif for reading from network, reading data from the network, and the one on the right shows the reading a block of data from within the data node. And we were able to annotate each of these traces with their runtime behavior and their performance characteristics. So now I want to go over some of the use cases of this tool. So one of them is compare and contrast different workflows, which means that we can compare and contrast different workflows, identify their similarities, and identify where they are different. We can use it for anomaly detection by filtering the frequent patterns and only looking at the non-frequent patterns. And also, we can use it to improve slow performance by, for example, finding optimization points for optimizing the system. And in summary, we believe that abstractions are powerful tools for building distributed systems, and we want to enable them for debugging distributed systems. We introduced workflow motif, which is a novel abstraction for debugging and diagnosis in distributed system. And our approach is to building workflow motifs using frequent subgraph mining tools. I'm done.